Hello everyone, hope everyone is doing well. In this lecture we are going to talk about sampling distributions. So one of the main aims of statistics is to find out some inferences of the population. So we want to know what is the population like. So in our case, let's say that as an example, we want to know the average income of US residents. Now I would like to know everybody's income in the US, and the US government does that every year. They collect data. Sometimes they actually try to do it monthly. But in our case, it does get hard because if I wanted to get the actual true population mean, then I would need to sample the whole population, or I need to find information about the whole population. Now, the problem is the US has over 330 million people. So collecting data on these individuals every month can get very difficult. It not only will take a lot of time, but also a lot of money and resources. So it gets very hard to calculate the population mean and the population standard deviation if my sample size is very large. Even if I'm looking at a small state, it still gets pretty difficult to collect all that information. So what the government does and what a lot of businesses do, and the same thing goes with businesses, because if I want to collect data on my customers, maybe I have 10,000 customers visiting my store every month. Even collecting all their information gets very difficult because a lot of customers may not want to be surveyed, or a lot of customers may be unavailable for surveys. And it's also collecting all 10,000 records can also be very difficult. So instead, what we do is we look at a sample from that population. A sample is basically, instead of looking at every single individual that's in that universe, sample is going to be a smaller section of the population. So what that means is we are looking at not everybody in the population. Instead of surveying 333 million, I will survey, let's say, 50,000. Now that means that some people might be like, well, 50,000 is too small of a number. It's still a huge a number of sampling or sample, but how is that possible that we can get information about the population that has a size of over 330 million from such a small sample? Even with businesses, let's say my N is 10,000, as we said in one of our examples. In that case, I could use an N of 500 in order to get some information about the population. And this is where some people may be like, how is this even possible? How can we use such a small sample to get inferences or information about such a huge population? So this is what we will do today. We are going to look at a very small example, a very simple example, to see how these samples can help us get information about the mean for a large population. 33.33. So let's use this as an example. Let's say my population size is 6. I have a very small population, and I would like to know the average of this population. Now, somebody knows this average. It's not us. We would like to find this average. But the average that I see in this population is 34. So I have this array of numbers, and I would like to find what the average is. Now, it would be nice if I could survey all the individuals and find that data, but it may not be possible because of type constraints or monetary constraints. Let's say my standard deviation is also, since we are using population standard deviation, we would say .p instead of .s, and we find those numbers. So this is my population standard deviation, my population mean. So knowing using the terms that we have learned already, instead of writing average, what I can write is I can go to symbols and I can include the population mean to be mu. And the population standard deviation could be sigma. So what I'll do is I'll write those here. So now we know that, okay, using mu and sigma, that these are our population averages and population standard deviation. But let's say I cannot survey every, as I've said, we may not have the ability to survey everyone. So let's say I just take a very small sample, let's say n equals 2. And I take different samples from my population. And just to make it simple, let's say there's sampling with replacement, which means that I can sample 31 twice. So let's say I go 31, 31, 31. So these are all my samples that I have that I could potentially survey. I don't know which one I would get because, again, this population is unknown to me. So I don't know which sample I could get. I could get sample 1, I could get sample 7, I could get sample 20, 21, one of those. Now each of those has a sample average. So we can write sample average and sample standard deviation. So we could do, let's actually move this a little down so that there's some space between those two numbers. And then we can copy the formulas all the way down here, and we have different numbers. So we have different sample averages and we have sample standard deviations. So in our case, well, we have our average is 34. Now, sometimes the average may be very low, 31. Sometimes it is very high, 36. So sometimes we do get 34 as average, but not always. Let us now draw a frequency chart. So here are my averages. Now let me draw this, or let me graph this, and then we can see what the shape is like. So if I insert a bar chart, in this case, we are actually including, if I want to rewrite them, this will be 31 to less than 32. We this a little differently, so we can say there is actually one that is 37. So now we have our graph, and we see that it kind of looks like a nice shape where we have the peak at around 34 to 35, which is similar to the average that we see here. The average, the population average, is actually 34, and our numbers, as we see, is we get a lot of the averages, or if I look at the frequency, 5 of the averages are around 34. If I look at closer to the numbers, so like between 33 and 36, we have 5 plus 4, 9, plus 3, 12 out of the 21 samples that I have are around that number. And now some numbers are way off, but most of the numbers are closer to the number, or to the population average. Now, if I actually added more sample size, so if I increased it from 2 to 3, I would get something even closer. So this gives us a very interesting, so what this theorem is telling us then, no matter what the underlying distribution that we have, it could be a normal distribution, it could be Poisson distribution, it could be any kind of distribution that we have, the sample average that we collect, that we have here, and that we have collected around, the sample average, they will be distributed and they will have a shape kind of like a normal distribution like this. Mine is not as nice, but if I had more observations and more, maybe I increase my sample size, it will have a nice bell shape, and the mean is going to be the same as the population mean that we have. And the standard deviation of this distribution is going to be the population standard distribution, which is sigma divided by the square root of the sample size that we are looking into. And this is what we call the central limit theorem. So again, just to recap, no matter what our distribution is like, because it could be any distribution, the underlying distribution could be anything. Once we find each of the sample averages, let's say we take a bunch of samples, and we find each of the sample averages, and we basically plotted this over in this graph. Once we do that, the frequency chart or the distribution chart will show or will look like a nice bell shape or a nice normal distribution. And the mean, this population mean, and the mean of this frequency chart will be very similar. So this population, the average, which I'll write x bar bar, will be very close to the population mean or equal to the population mean. And the standard deviation of this frequency chart will be equal to this value here, sigma over the square root of the sample size. So now we can actually call this theorem something. So this theorem is called the Central Limit Theorem. And it is a very important theorem with which we actually can base our samples out of, because when someone asks us why are we taking such a small sample, well, if we keep on repeating our survey over and over again and we average those samples, then we will get closer and closer to the population average. If I look at the sample average is of all these sample averages, if I try to find the average of this sample, I will find it to be, let me just write here. So I will name it average of the averages, or average of the sample averages. That would be, which is actually 34. And the standard deviation would be of the population, or of each of the sample averages. If I take the average of that, which I get to be is 1.67. So if I take the standard deviation of the population and divide it by the square root of n, or the small n, which is 2. So let's try that. I should get something very close to that, as you can see. Now, if I had something a little different, if I added more, instead of taking a sample size of 2, if it was 3, I would have a slightly better answer, or slightly closer answer. But this gives us some hope that even though I may not have the ability to survey all the people in the population or all the entities in the population, what I can do is I can take samples, and every sample that I take will, and if I average them, it will lead me closer and closer to the population average. And this is what I get here, which is kind of cool. Now, one of the things we can do is that, as we saw here, that not all the averages are close to the population average, which was 34. Some are very low, like 31. Some are very high. We saw one to be as high as 37. So in that case, we would like to know, is there a range? So is there going to be a range with which we can talk about it? In other words, we may want to know 95% of the time, or we may change it to 90% of the time, or 99% of the time. What range will the averages or sample averages look like or be in? So this is my average, or the population average and population standard deviation, and I'm considering to use a sample size of 2. Now the formula for that is going to be, it will be a little bit of a, so this is going to be the formula for that. So we are going to find out what is mu. We know mu is 34. And this number that we have, z alpha over 2, this is from the z values. So if I am 95% confident, or if I want my number to be 95, then alpha is actually 1 minus 95%, which would be 0.05. So alpha here, it's basically equal to 1 minus the range that we are looking at. So we'll call that the confidence interval. So in our case, the alpha is going to be 0.05. Since I'm dividing now by 2, so alpha here is going to be 1 minus 0.95, which equals to 0.05. But I'm actually asking for z alpha over 2, so which comes out to be z of 0.025. Now what is the z? The z is the z value that we can find from the normal distribution. So what I can do is find z, or norm dot s dot inv. And the probability I'm looking at is 0.05 divided by 2. And I get a number 1.95594. So I want to be 95% sure that my sample averages are going to be within this range, or within this range. So the alpha here is like telling us what is outside of that range. So if you look at since we're looking at a normal distribution, this is what my distribution is kind of looking like. So it is going to be of this shape. So it is going to be of this shape. So my distribution is within this range. Now I need to find out the cutoff values. Where is it? What is the range it's going to be between? This is going to be my 95% confident. So I'm going to be 95% confident that I'm within these two range, let's say. Then the leftover is going to be 5% leftover. Now I can put all 5% on one side and all 5% on the other side. So what I do is I distribute it. So 2.5% is going to be on the left and 2.5% is going to be on the right. Now, how do we calculate the confidence interval? So I copied this part of the formula here, right here. And this part has a name. We normally call it the margin of error. And so I know what the numbers are, so I can just plug it in. So it's my z value that I found, which is just giving us the extent of the range. And then we multiply that with our average, with our standard deviation, divided by the square root of the sample size. So with that, I'm going to, since the number is negative, I'm going to put a negative value here just so that the margin of error comes up to be positive. So with that, we have our margin of error. Now what I have to do is I have to add it and subtract it from the mean. So the mean is given here is 34. So what I'm doing is I'm subtracting the margin of error from the mean. So it will be equals to the average minus the margin of error, and I get 31. And the upper bound is going to be the average plus the margin of error, which is 36.99. This means that with 95% confidence, I can say that if I have samples with sample size of 2, n equals 2, then for 95% of the time, the sample averages will be between 31 and 36.99. So which is kind of nice to say. In other words, we can say that if we run this experiment, if we take 100 different samples from this population with n equals 2, then for 95 times, or 95% of the time, if the sample average is 2, the averages will be between 31 and 36.99, slightly above 31 and less than 37. So it's giving us then some idea. If I knew what the population mean is, then this is where 95% of the time our sample averages are going to lie. So this gives me some idea that, like, if I take samples from my population, even though I may not know the sample or the population average, by repeating the experiment over and over again, or by repeating the survey over and over again, I can get closer and closer to the population mean. Hope this was helpful, and I will see you at a later lecture. Have a good day.